Hello, my name is Walker Brown, and this is Physics 2212, Lab 5, Faraday's Law. In this lab, we will have an introduction, an overview of our experiment and our results, our glow script model, and then finally a discussion of our results. So, in this lab, we'll collect data on a magnet falling through an aluminum tube to observe Faraday's Law. We'll use a magnetometer to find the north of the tube and then drop the magnet through the tube. Then we will calculate the time it took the magnet to fall through the length of the tube, and we will repeat it for 5 trials. And a quick preview of our results show that our experiment took 1.25 seconds to go through, and then computationally it took 1.17 seconds to go through. For this lab, we'll need to know Faraday's law, Biot-Savart's law, Ohm's law, the loop magnetic force, and that EMF is equal to the change in flux over the change in time. It's the differential form. We'll assume that air resistance is negligible and that there are only 2 forces acting on the magnet, being gravity and the magnetic force. Here's a quick diagram showing it. So the magnet is pictured right here with magnetic north and south, and then we'll measure time in and time out as we drop the magnet in, and as you can see, we have the magnetic force as well as the gravitational force shown here. So for some measurements, the length of a tube is 0.3 meters, the aluminum foil width is 0.01 meters, the inner radius of the tube is 0.02 meters, outer radius 0.03, the magnet mass is 0.03 kilograms, and the average fall time was 1.25 seconds. So some quick checkpoint questions. Why can't we use a ferrous tube? Well, ferrous means it contains iron, which will interfere with the magnet, therefore changing our times. What happened to the magnet? How does it compare to the magnet with no tube? Well, the magnet in the tube falls slower due to the opposing induced magnetic force due to magnetic flux, also known as Faraday's law. Here's our computational model. Feel free to pause and parse through for specific coding questions. Also, the code will be posted in the description. Here's our results. As you can see, it took 1.17 approximately seconds for the magnet to fall through the tube, and feel free to pause and take a look at the graph. And also in the computational model, feel free to look, this magnet actually does fall down the length of the tube. So some possible sources of error were some possible rounding errors or some off early calculations that would account for the differences between our real life scenario and our computational one. And some lingering questions. What if the resistivity of the conductor were reduced to as close as possible to 0? How did that dynamics of the falling magnet change? Well, the braking force would increase to the point of being almost equal to the gravitational force, causing the magnet to fall much slower. What if holes or slots were cut into the tube? How would this affect the ring's currents in your model? Well, the induced current would likely decrease as the new holes would disrupt the current, decreasing the magnetic force. The magnet would fall quicker as a result. All right, everything. Thank you so much. I really appreciate it.